KCET 2026 aspirants. So here are some few questions to think in the starting of this session. So have you ever thought why this chemical DDT was the most discussed chemical or most I can say talked about chemical in the history of chemistry? Or have you ever wondered why this chloroform, which was earlier used as an anesthetic, is now completely banned? So welcome back to the Sankalp series, where we have taken a pledge to work every day, to put our 100% efforts every day to get top 1000 rank in KCET 2026 examination. So starting from the weird reactions of haloarenes to the real life use and misuse of polyhalogen compounds, this video consists of concept clarity and power pack MCQs. And let me tell you a very good news. So this video is going to be the last part of this most important first chapter of Haloalkanes and Haloarenes. So we will be completing this chapter today. Okay, so kudos to all of us and kudos to all of you that we have worked hard, we have watched all the videos, we have replied in every comments, every videos, every answers, and today we will be ending this chapter. Okay, so now today's class is just not going to be chemistry, but it is where the real organic compounds, you will find their real uses in the real life, where we actually use them, what are their purposes, what are their harmful effects, everything we'll study in detail. Okay, so tighten your seat belts and let's get started. But yes, I do remember, before starting the session, it's time to congratulate, to recognize, to appreciate all the children who were involved, who listened the whole class, who were very active during the last class. They have answered the homeworks, whether it is correct or wrong. They have put down their scores. They have appreciated me for my teaching. So it is a way to thank all of you. I'm really grateful, and the level of this involvement is increasing day by day. In everyday class, I see the number of comments are increasing, and that is something which is really motivating, and a very, I can say something, I am very thankful to all of you. Okay, so yes, now let's go to our section where we will be congratulating all the students, and I'm very happy some of the names are coming new, whereas some of the names are consistent from the very first video of this session of this chapter. So that says that the students are consistent with me, with the lessons, with the portions, right? So here we are with our KCET winners. So I'm calling all of you as the winners, because when you put your efforts every day, your hard work will never go into vain, and you will be getting a very good seat, a very good rank in 2026 KCET examination. Just you need to be consistent like this for this next 1 year. Okay, so yes, now it's time to welcome all my children who have really made me proud, who have really showed their involvement in the classes. So first of all, I have some new students also, so I'm very happy that new students are also joining. So you can also share these videos if you find that the lecture was helpful, if the questions were helpful, they were interesting, do share it with your friends. Okay, so first of all, we have Austin. So he's a regular viewer of, I have received his comments in almost all the videos. So ma'am, wonderful sessions, all concepts are very clear. So thank you, Austin, and I'm really grateful that the videos are helping you. Next we have here Marudesh Goda. He has answered, I have given a question why the tertiary carbocations are more stable. So that is due to the stability of tertiary. The question was which carbocation will be more stable and why. So that is, the answer was tertiary carbocation, and he has answered, and this question was in between the session. So he has taken this effort to put down in the comment section the answers while watching the video, which is really commendable. Next we have again Marudas has also given all the answers of the homework questions. Okay, and do not worry students, I will be discussing all the 3 answers in today's class, so please check down your answers and you will be getting all the answers. Okay, next we have here Nitya. Nitya is also a student who has been consistently answering all the videos, very regular student. So Nitya has also given this answer due to the stability of carbocation, the question which was asked in the video, and also has put all the answers for homework questions. So 3 homework questions, 3 answers are given. So thank you dear, and these small efforts that you are putting in this video, in making this video making more interactive to talk to me, this is really appreciable. Next we have Sarwar Hussain K. Okay, he has also given the homework answers. Then Astin has also given the homework answers. Next I have this student, also he is a regular viewer. We have Ashwini Veneers. Okay, every time I'm not able to pronounce this name properly, but I hope you would forgive me and you would be very happy that I have taken your name as well. So homework questions he has also answered. And then we have Sagar Anmol. He has so many comments, but I took only few of the comments because of the space constraint. So he has given all the rounds answers, he has given homework answers. So Sagar, very like a big round of applause for you for being so much consistent throughout the video. Then we have Nitya S, who has also given that I have scored 5 out of 5. So we have rounds in the sessions. So C has also given, and Bhuvan has given the total score of 25 questions. He has secured 23. So Bhuvan, that's really great, and I'm very sure that your concepts will be getting stronger and stronger as you study more. So do not worry, these 2 marks that you have lost, please make sure what questions you got wrong, why you got wrong, and analyze them. Next we have again Bhuvan here also has given round 1 5 out of 5, and Sagar has got 25 out of 25 in the last session. So that is again really appreciable, and these all students, a big thank you to all of you. Okay, so you all deserve, you all have a very special place in my heart, and I really wish that you should be getting the best, everything best in this world. Okay, that is my from the bottom of my heart, my wishes for all of you. Okay, so fine, so we are done with this, and I hope these numbers increase, that I need to take at least 2 to 3 slides to cover all your names. And don't worry, I will be doing that whatever time it takes. I'll be putting each and every one of your comments, so do comment down your answers. Okay, so next there is I have seen homework answers, many of you have answered. There are some things, some questions you have got it wrong, some questions you have got it correct. So let me discuss all the answers and you can just revise your homework answers. Okay, so the first question was the increasing order of reactivity in the SN2 hydrolysis of the following alkyl bromides is. Okay, so the question is asking the order of SN2 reaction. Okay, and what is the order of SN2 reaction? So we know that SN2 reaction order is 1 degree, 2 degree or 3 degree. Okay, and then 3 degree. And if there are both 1 degree or both 2 degree, it should be proportional to less steric hindrance, means where the molecule is small, there the reaction will be faster. Okay, so now let's see, we have tert butyl bromide. Okay, tert butyl bromide is like this. Okay, so this is, if you say this is a 3 degree one, then you have methyl bromide. Methyl bromide is simply like this. Then you have, this is primary. Then you have secondary butyl bromide. So secondary butyl bromide is a compound like this. Okay, so this is, as you can see, it is a secondary. Then you have N-propyl bromide. So it is like this. Okay, now what we can observe here is this is also primary. Okay, now you can see that we have 2 primaries, 1 secondary and 1 tertiary. So by order I can definitely find that the tertiary one will be the least one according to this order, right? You have to find increasing order, means the lowest one will come first, then the highest one, right? So this, the one should be lowest, so I have these 2 options, I can eliminate these 2 options. After tertiary I should have secondary, right, according to order, 3 degree, 2 degree. So that is my one. After that I should have 3. So here I have 4, so I can eliminate this one. So this should be my answer. But let's check here. Okay, here I have both primary. Then ma'am, how we will decide when we have both the groups primary? So the smaller the group, more will be the reactivity. Okay, higher will be the reactivity. So if you see here, only 1 carbon is there, here is 3 carbon. So which is a smaller group? This one is a smaller group, right, the methyl bromide. So that will be the highest reactivity, then this one will come. So correct answer will be option number A here. Okay, moving to the next homework question, which one of the following can occur in an enantiomeric form? So enantiomeric form, it will occur if that carbon is optically active. Okay, okay, if it is optically active, means it should have a chiral carbon. What do you mean by chiral carbon? A carbon with 4 different groups. A carbon with 4 different groups. So here can we see that I have 4 different groups? Let us check. We have 2 methyl groups. So this will not be the answer. Here can I see? Yes, I have 1 hydrogen, 1 acetic group, 1 have ethyl group and 1 I have methyl group. All the 4 groups are different. So this compound will be optically active and its mirror image will be non-superimposable, okay, and both of them will be enantiomeric pair. So here the answer will be option number B. Now coming to here, you can see both groups are H, all the 4 groups are not different. Here also I can find 2 H groups, all the 4 groups are not different. Okay, so answer will be option number B for the second question. Okay, next this question I think I haven't discussed, or I am not very sure, but I'll tell you, we have talked about beta elimination, right? And for beta elimination, I forgot to tell you about the reagent, means which reagent we can use. Okay, so for reagent it is always alcoholic KOH, or you can use alcoholic NaOH. Okay, so that is the first one. Next, you can use any base, any type of strong base can be used. And when I talk about base, you should remember all the ammonia and its derivatives, ammonia plus its derivatives. When I tell derivatives, what I mean, when I'm saying derivatives, this H groups are replaced with R groups. Okay, so the ammonia and its derivatives can behave as also as a base. Clear? So aqueous NaOH, no. Alcoholic KOH, yes. So here you can see ammonia, this H is replaced with R group, so this is also there. So both B and C. So the correct answer will be what? We will have option number D here. Okay, clear? So the option number D is the correct answer for this question. Fine. So now we will be moving to today's class. So till now we have met what all things we have studied till now. We have said hello to our halo. So in the first part we have a brief introduction about the haloalkanes, haloarenes. We came to know how we should nomenclature them, how we should classify them, right? In the second part we studied about the preparation and the physical properties of haloalkanes. We were in the lab where we were preparing about these haloalkanes and haloarenes. In the third part we studied about the reactions of haloalkanes, the SN1 reaction, SN2 reaction, right? Then what is an chiral molecule, what is enantiomeric form. So we had these type of discussions on the third part. So in today's part we will be talking about the reactions of haloarenes. Okay, so today, this last time it was haloalkanes, and today we will be having the reactions of haloarenes. Means what is haloarene? You remember what is haloarene? When you have a benzene ring and you have a X group. Okay, so this is a haloarene. So we will be today studying all the reactions, means or what all compounds we can add to this haloarenes, and then what type of reaction it will show, what will be the product of these type of reactions. Okay, so we will mix them, and today you will see my reaction. So this is our cute little haloarene. So do comment down how is our chlorobenzene looking, is it cute or not. So this haloarene we will be seeing its reactions. Okay, let's move to our next one. So today's part, 2 things we will be covering: reactions of haloarenes and polyhalogen compounds. Okay, so this is an important part from where here many questions can be expected. So do listen properly. Clear? Okay, so now we as we have seen in case of haloalkanes, there were 3 types of reactions. So quickly comment down what were the 3 reactions of haloalkanes. Okay, so this questions that I am asking in between, that is to test you how much you have remembered from the previous class. Okay, you can just refer your notes also, you can answer what were the 3 types of reactions of haloalkanes we have studied. Now we will be seeing the 3 reactions of haloarenes today. So that is nucleophilic reactions, electrophilic reactions and reactions with metals. Okay, nucleophilic reactions, electrophilic reactions and reactions with metals. Now coming to The first one, that is nucleophilic reactions. So here our little boy, this is you all are this child, okay, who is very confused about today's class, what all things are there. So the first question that arises is, do haloarenes undergo nucleophilic reactions? So in the last class we have seen that haloalkanes were undergoing nucleophilic reactions, and there were two types of nucleophilic reactions mechanisms, SN1, SN2, right? So haloalkanes were very happy, they were undergoing nucleophilic reactions. But what about haloarenes? Do they also undergo nucleophilic reactions or not? We will be discovering in this part. So first of all, I'll show you an image. So what do you think by seeing this image? This is a nucleophile, right? I have shown you this diagram in my last class. This is a nucleophile, and this is our cute little chlorobenzene who was smiling in the previous slide and now suddenly has become very angry, right? So what can you assume by seeing this particular image? So here we will be discussing that the haloarenes, okay, the haloarenes are not very fond of nucleophiles. So they do not undergo nucleophilic reactions easily. Okay, now we will be talking why and what, but there is a very basic reason that you should understand. So let me first take the concept of haloalkanes. In haloalkanes, what we had are X, right? X was delta minus and this was delta plus, and then nucleophile was there which was electron deficient, electron rich, and this was electron deficient. So this attacked on this one and we got a compound like this, right? This was the case. In case of haloarenes, what we have, see, just imagine now, you have this one, you have a benzene ring, okay, and you have this X group, and then you have nucleophile, right? So this nucleophile has to attack here and this X has to go. Now this is this benzene ring, okay, which is very angry now. We have to find out why. So now see, this nucleophile is electron rich, okay. In Rx, this R was electron deficient, right? But here what happens, in benzene ring there are pi electrons, right? You can see so many pi electrons are there. So if you see the benzene structure, it is like this. This is benzene, this is electron, this is also electron cloud. So what I can say is, if a benzene ring is there, it has electron cloud above it, it has electron cloud below it. So this benzene ring is not delta plus, it is not delta plus, it is also electron rich. If this is already electron rich, will it again attract a nucleophile? Why? Because this is negative, they will repel each other, right? So that is why you can see this repulsion, this angry, this fight between a chlorobenzene and a nucleophile. So that is why they will not react easily. I hope this is clear. So nucleophiles, okay, just imagine, in case of Rx, haloalkanes, this R was delta positive, okay, this was delta minus, this was delta positive. So that means what? These was electron deficient and nucleophile was electron rich, so it was easily attacking on this R group. But when we compare haloarenes, okay, this ring was, haloarenes was, what I can say, this is positive, this is electron rich. Because of, what is the reason why it is electron rich? Because of these pi bonds. It has electron cloud above it, below it. So these electron clouds are present. So a nucleophile is also electron rich, benzene is also electron rich. So there is repulsion between them, and that is why nucleophilic reactions are not easily happening in case of haloarenes. I hope this is clear. Okay, so we have got the conclusion that nucleophilic reactions, so what is the answer here? Do haloarenes undergo nucleophilic reactions? What is my answer here? Not easily. Okay, not easily. So we will see next here. So we have this cute little chlorobenzene saying hi to all of you. So I want all of you to say a hi to this chlorobenzene, okay, this cute little chlorobenzene. So he is saying that I don't undergo nucleophilic reactions easily. Here's why. Okay, there are some important reasons as well other than that what we have discussed. So we will be seeing 3 important reasons other than what we have seen. So the first one is your resonance effect. The second one is difference in the hybridization, and the third one is the instability of phenyl cation. So now let me first take you through the mechanism. So what basically was happening, see, Rx was there, okay, Nu comes, okay, this attacks here and this goes, so there is a breakage of Rx bond, right? This Rx bond has to break, and in place of X the nucleophile should come, right? Similarly, if you have Ar and X, so this ARX bond has to break, okay, but that breaking, this ARX bond breaking becomes very, very difficult due to resonance effect and difference in hybridization, which we will talk in detail, okay. So what does these two affect, these two factors, what they do, they, because of these two factors, the ARX bond cleavage becomes, we will see how, okay, we will understand the mechanism, but just for now you have to get this one, that for the substitution, nucleophilic substitution reaction to happen, this ARX bond has to break, but and in place of that X, nucleophile should come, but this bond breaking itself is very difficult due to these two factors, and we will see that in detail, okay. So the first one, if you see the resonance effect, so in haloarenes what happens, the electron pair on the halogen atom are in conjugation with the pi electrons of the ring. So what happens, the CCl bond acquires a partial double bond character due to resonance. As a result, the bond cleavage in haloarenes is difficult than haloalkanes, and therefore they are less reactive towards nucleophilic substitution reaction. Now you might be thinking, what ma'am, you have read the whole paragraph, you didn't understand anything. So don't worry, I will explain. First you should understand one thing, that breaking, I'll write here, breaking single bond, okay, breaking single bond is easy than double bond, okay. So we have here Rx and here we have ARX. Now this is also single bond, this also looks like a single bond. But let's see what happens after this. So if you see, this X group here has a lone pair, okay, there are 3 lone pairs present, and now these lone pairs undergo resonance. So as a due to this resonance, you can see a small, or I can say a partial double bond is formed here. This double bond is not a permanent double bond, but due to this resonance, what happens, a partial double bond is created. Okay, now since this partial double bond is created, what will happen, we have just discussed that breaking this bond will now be difficult. So when this nucleophile comes, okay, first of all, when this nucleophile comes, you can see that it is saying, okay, here there is a double bond, I cannot break that double bond, I have the power to break only single bond. So nucleophile sees that there is a double bond and it cannot break, so nucleophile goes back. Okay, so that means that is why this nucleophile cannot break this CCl bond or CCX bond due to a partial double bond character. Now why do we say it as a partial double bond character or partial double bond? Because it is not a permanent double bond, okay, but due to resonance this bond comes, okay. So it is present sometimes, it is not present sometimes, but due to resonance that double bond has come. It was not originally present between carbon and chlorine. Clear? First reason. Second reason, we will see the difference in the hybridization. Now understand this one. In Rx, so if you see, first if we compare Rx, we have Rx and we have ARX. Okay, now this carbon has 4 single bonds, right? So 4, I am writing just like this. So this carbon has 4 single bonds, so it is sp3 hybridized. And if you see this carbon, it has, if you see this carbon, it has 1, 2 and 3 single bonds, so it is sp2 sp2 hybridized. Okay, the hybridization of this carbon is sp2, hybridization of this carbon is sp3. So now let's see what happens due to the difference in hybridization. How does it what results happen, or what are the consequences of the difference in hybridization? So in haloalkane, the carbon attached to the halogen is sp3 hybridized, while in case of haloarenes, the carbon attached to the halogen is sp2 hybridized, that we have seen. The sp2 hybridized carbon with a greater s character. Okay, so now this, let's see, if I have sp3 and you have sp2. Okay, so you have to say what is the in this bond formation, in this hybrid orbital, what is the percentage of s. So there are total 4 orbitals. There are 3 p and 1 s, so total 4 orbitals. 100 divided by 4. So what is the percentage of s here? 25%. How did I get? 100 divided by 4. Here you can see there are total, in this sp2 hybrid orbital, there are total 3 orbitals are present, right? So then what is the percentage of s? So what you have to do is 100 divided by 3, which we will get around 33.33. So you can see here the s percentage is 25%, here the s percentage is 33.33. So that is what is told. The sp2 hybridized carbon with greater s character is more electronegative and can hold the electron pair of CX more tightly than sp3 hybridized carbon in haloalkane with less s character. So what I am saying, see, this CX is there and we have this CX. Okay, so this is sp3 carbon and this is sp2 carbon. So the here there is less s character, here there is more s character. So less s character means less electronegative, and here more s character means more electronegative. Okay. Now if this one is more electronegative, what will happen? If this one is more electronegative, this bond, okay, this bond will be very strong again. When there is more electronegativity, see, this is also X, this is also more, this is electronegative, this is electronegative. So both will be pulling that electrons towards themselves. So those electrons are tightly bound between these 2 electrons. Now here what happens, this is very less electronegative, X is highly electronegative, so the electrons are towards X. So this bond can easily break. But here there is strong force of attraction for both the bonds, for both the electrons. Nobody is trying to leave the electrons because both are electronegative. So this bond is very, very strong. So again, when nucleophile comes here, he founds that okay, X is also fighting for this, this is also fighting, this bond is very strong, I cannot break it, right? I cannot break it, and this Nu goes away, right? So the CCl bond length in haloalkane is 177, while in haloarene it is 169. So since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. Okay, so when we have, what is the reason for this bond became, second reason for this bond to be very, very strong, that is the sp2 hybridized carbon present in haloarenes. The first reason was they have a partial double bond character. That is the first thing. Second, this bond is also very strong because it is attached to a sp2 carbon. Okay, so we can see here, this is your sp2 carbon, this is your sp3 carbon. This bond is very strong because of higher electronegativity of this carbon. This bond is comparatively weak because of the less electronegativity of this sp3 hybridized carbon. Now moving to the third reason is something, you can see this figure, instability. Okay, instability of the phenyl carbocation. So when you see, if I have Rx, okay, when this X goes, we get a carbocation R plus. Okay, similarly, if I have this phenyl group or I have this haloarene group, okay, when this goes, we will get a carbocation like this. Okay, now see, this carbon is sp2 hybridized, it is electronegative, and always remember, positive charge on an electronegative atom is highly unstable. If you have F minus, negative charge on an electronegative atom is very stable, but when you have F plus, this is very unstable. O minus is stable, O plus is unstable, N minus is stable, N plus is unstable, right? So having positive charge on the electronegative atom makes this phenyl carbocation very, very unstable. So that is why why this bond does not break. Okay, so in case of haloarenes, the phenyl cation formed as a result of self ionization will not be stabilized by resonance. Okay, so there is no stability for the phenyl carbocation that is formed. So because of these three reasons, the haloarenes are not very comfortable with nucleophiles, or they are not interested to react with the nucleophiles. Okay, but does that mean haloarenes does not react? Haloarenes does not react. Does that mean haloarenes does not react? Big question here. Haloarenes does not react or they react. So now haloalkanes and haloarenes. Haloalkanes are reacting with nucleophiles. Now haloarenes saw that, okay, I have this problem, I cannot react with nucleophiles. But can I be defeated by haloalkanes? Can I accept my defeat from haloalkanes? Then haloalkanes will say that I am more powerful because I can react with nucleophiles. You are not powerful because you cannot react with nucleophiles. So thinking that there is a special, then haloarene started using his brain. How can I react with nucleophiles? How can I react with nucleophiles? Then he found something that we will understand in the next segment. So here again we have our cute little chlorobenzene who says that no, I will not accept my defeat from haloalkanes. Okay, I am also as much powerful as haloalkanes. I can react with nucleophiles, but there should be some special conditions under which I can react with nucleophiles. Okay, so what is this answer to this my previous question? Does not react? No. Okay, it reacts, but under special condition. Okay, it reacts under special conditions. So we will see now what are the special conditions, or what we can do so that our haloarenes is not defeated by haloalkanes. It can also react with nucleophiles. Okay, so let's see that. Okay, so the first condition is you can use very high temperature and high pressure. 623 K and 300 atm at this much high pressure and temperature, what will happen? This bond can break. Okay, so in that high pressure and temperature you can easily give, you can see this NaOH. If you remember, what nucleophile will this generate? This will generate OH minus, and this will attack and this will go, and we will get this one. Okay, so first condition that we can do is what? To at high temperature and pressure. Now I have told you in the starting of the class today that here this benzene ring, okay, this R group is electron rich, and when you have a nucleophile here which is also electron rich, so there is a repulsion between them. So can I do something to reduce the electron density of the ring? Can I do something to reduce the electron density of the ring? Think, can we do that? Is there any way that I can reduce the electron density of this ring? Now this becomes electron deficient. Now nucleophile is electron rich, so they can have a reaction, right? So yes, there is a way how we can reduce the electron density of the ring. How can we do that? We can do that by adding electron withdrawing groups. Okay, how we can do that? By adding electron withdrawing groups. Now if you have remembered, in class 11 we have some electron donating groups, electron withdrawing groups. Electron withdrawing groups are those groups which will withdraw the electrons from this ring. So if these electron withdrawing groups are withdrawing the electrons from the ring become electron deficient. Okay, now when it is not having electrons. Okay, now for example, there is two rich people. Okay, there is rich people 1 and rich person 2. Okay, they both are very jealous of each other. They are not friendship, they are not having any good friendship, nothing. Now a robber came and looted the money of this one. Okay, then what will happen? This person became poor. Now when this person has become poor, it will want help from this one, that please, my money is over, please give me some money. There will be friendship between this team, there will be reactions between these two. The same thing happens here. So when this electron withdrawing group is attached to the benzene ring, they steal the electrons of the benzene. Now benzene, which was earlier electron rich, has now become electron poor. Now it will ask nucleophile, please help me, please give me some electrons, and that is why this ring and this nucleophile will react with each other. Clear? So what is our tactics? We have two tactics. What are two special conditions? One special condition is giving very high temperature, high pressure, okay, but that is not always possible, right? You cannot have that much apparatus to give very high temperature and pressure. The second other way, or the effective way, is to add an electron withdrawing group. When you add an electron withdrawing group, the benzene ring becomes poor in electrons. Now it asks help for nucleophiles. My one group has come, one robber has come and stolen all my electrons. Please give me some electrons. The nucleophile will come and they both can react, right? I hope you are getting this. Okay, so let's see now what electron withdrawing group we can attach. So the first electron withdrawing group, the most common electron withdrawing group we are attaching is NO2 group. Okay, so if I attach NO2 group, you can see that the reaction which was taking place earlier was 623 Kelvin can now take at a lower temperature. Okay, now if I add more electron withdrawing group, I'll add one more electron withdrawing group, the reaction can take place at a further lower temperature. If I add 3 electron withdrawing groups, see, here you have made little bit poor, so little bit nucleophile will help. Here more poor is there, right? The electron density has decreased much more, so nucleophile will help easily at a lower temperature. Here this, you have completely robbed this benzene ring, okay? It has no electrons of itself. All these 3 NO2 groups has robbed the benzene ring, has stolen all its electrons. So what will happen? With a little bit of water also the reaction can take place. So what is the reaction happening? The chlorine group is replaced with the OH groups, right? That is the reaction happening. Clear? So now if I, okay, now have you observed something, that we have added NO2 group, no doubt, but at what position did we add the NO2 group? That is the next question. We have added the NO2 group only at ortho and para position. Did we add at meta position? Did we add any NO2 group at meta position? Only we have, here we have para, here we have ortho, here also ortho and para. There is no NO2 group at meta position. Is there any reason for that? Let's find out. Okay, fine. So now if you see how, so I have told you that this NO2 will steal the electrons of the benzene ring, right, and will make this benzene ring a poor fellow. So how it is stealing, where is the pathway, how it is, where, from which door it is entering and stealing the electrons? Let's see. So first of all, you can see that what happens, this electron which is present here can move here, okay? So there is a negative charge on this one. Next, these electron can move here. Okay, so now you see this is benzene electrons, right? It can move here. So now after that, this electrons are on this carbon. Then these electrons can come here. Okay, now these electrons are on this carbon. So these 2 electrons are on this carbon. Now these electrons can further go to nitrogen now. Okay, and here. So the electron which was present here has now come to oxygen. So what I am saying here is, the electrons that were present here, they came here, the electrons that was present here, they came here, and after that they traveled and reached to the NO2 group. So NO2 group has stolen the electron from the benzene ring, right, when it is present at the para position. Now what happens when it is present at the ortho position? Again these electrons come here, come to this carbon, then from this carbon the electrons can go to NO2. Okay, so when will these electrons move? You know what is the condition for resonance? You need to have single bond, double bond, single bond. Whenever you have this type of condition, okay, or double bond, single bond, double bond, then electrons will move. So now you see when this electrons have come here, okay, you can see here, I'll just erase. Okay, so you can see there is a double bond, there is a single bond, then again there is a double bond, single bond, double bond. In that case the electrons can move, right? Here if you see, you have double bond, single bond and double bond, so the electrons can move here. So when it is present at ortho position, when it is present at para position, it is able to steal the electrons and it is making the ring poor in electrons. So the ring is now seeking the help of nucleophile. So when the nucleophile comes, it will react easily. Let's see now what happens when we have meta position. So here this our cute little chlorobenzene is saying the effect is pronounced when NO2 group is introduced at ortho and para position. Okay, so we will check now what is wrong at meta position. Okay, so remember for now meta position, what happens? The electrons come here. Okay, so electrons come here, we get electron here. Now the electrons are coming on this double bond. Okay, the electrons are coming on this particular carbon. Here I am getting a double bond and then electrons are moving here. The electrons are not coming to this carbon. If the electrons are not coming to this carbon, then how will NO2 steal that electrons? If you see the previous two cases, you see in the previous two cases, here the electron came first, then the electron came here, then the electron came here to the carbon where the nitrogen is bonded. Then only it can steal from here, right? If here also if you see, this electrons have moved here to this carbon, the carbon where the NO2 is bonded. This carbon should have electron, then only NO2 can steal. But when I am having in meta position, these electrons are first coming here, then that is coming double bond here, then here if you see, it comes here, then this electrons move here. There is no place or no position where this carbon has the electrons. So if this carbon is not getting electrons, the NO2 cannot steal the electrons, it cannot reduce the electron density. So that is why if NO2 group is present only at ortho and para position, then only it can steal the electron, it can make the benzene ring poor and the nucleophile can react. Okay, so where the NO2 group should be present at ortho and para position. We will see, however, no effect on reactivity on haloarenes is observed by the electron withdrawing group at meta position. So the reason is very simple, because the NO2 group is not able to withdraw the electrons from the benzene ring if it is present at meta position. Okay, fine. Now let's see the next thing. Can you think why does NO2 group shows its effect only at ortho and para position and not at meta position? So we have discussed this in detail, but I have a point wise answer for you also. See, the presence of nitro group at ortho and para position withdraws the electron density from the benzene ring and thus facilitates the attack of nucleophile on haloarenes. So whenever this electron withdrawing group is present at ortho and para position, then only it can withdraw electrons and it can facilitate the attack of nucleophile. The carbocation thus formed is stabilized by resonance. The negative charge appeared at ortho and para position with respect to the halogen substituent is stabilized by the NO2 group, while in case of meta-nitrobenzene, none of the resonating structures bear the negative charge on the carbon atom bearing the NO2 group. So in meta position, if it is there, when you draw the resonating structure, the carbon which contains the NO2 group never gets the negative charge. When it does not get, NO2 cannot steal. Okay, so that's the whole conclusion here. So we have understood till now what? Three things, two important things we have studied now. That haloarenes are not very much active towards nucleophilic reactions. Okay, so there are main three reasons for that: resonance effect, hybridization of carbon, and instability of phenyl cation. But still, now haloarenes doesn't want to get defeated by haloalkanes, right? It doesn't want to be like, I am less powerful than haloarenes. So haloarenes finds two ways to react with nucleophile. The first way is at higher temperature and higher pressure, which is not a very preferable way, and the second easier method is to have some electron withdrawing groups around it which can withdraw the electrons, which can make it poor by electrons, and then it can react with nucleophile. But these electron withdrawing groups should be present at ortho and para position only. Okay, I hope this much is clear. Now we will move to the next reaction, that is electrophilic substitution reaction. Okay, so electrophilic substitution. So now when I said you that if I have this nucleophile, sorry, if I have this haloarene, okay, and I have told you that this ring itself is electron rich. Why? Because in the benzene ring there is electron cloud, so this is electron rich. So this can easily react with electrophiles, which is electron deficient, right? So that is why all the benzene molecule can show you electron, all the haloarenes will show electrophilic substitution reaction. So here what will happen? Any of the H will be replaced by this electrophile. Okay, so we will see what all reactions it can show. So haloarenes undergo the usual electrophilic reactions of the benzene ring, such as halogenation, nitration, sulfonation and Friedel-Crafts reaction. Okay, so we will be seeing these reactions. Now halogen atoms, beside being slightly deactivating, okay, it is a if you see, what is this? Cl, right? So it is electronegative, it will pull the electron towards itself, so it is making the ring slightly deactivating. Okay, is ortho para directing, therefore further substitution occurs at ortho and para position. So what, but still it also donates electron, it has plus R effect, it is a electron donating group, it is a minus I effect. Okay, so what happens here is whatever substituent, whatever E plus will come, it will attach at ortho and para position only. Okay, so you can see, if you see the resonating structure of this one, you see the bond is coming here, there is electron density here, then again this bond can come, there is electron density here, then again this electron density is here. So where is the electron density? Ortho para positions. So when you have this electrophile, it will attack at that position where the density of electrons is high, right? This is electron deficient. It will attack at electron rich species. So at ortho and para position there will be substitution reaction happening. So further, the halogen atom, because of its minus I effect, has some tendency to withdraw the electrons from the benzene ring. Okay, so because of this, because of its plus R effect, because of its electron donating nature, it will direct the incoming electrophile to ortho and para positions, but it also deactivates the ring because it has minus I effect. So now if I compare a normal benzene, okay, and a normal haloarene, and you have an electrophile here, which will be more reactive to this one. Now see, this one, okay, this one can react easily, but this is having, it is electron, it is withdrawing the electrons. So this ring, if I compare these two rings, this ring is much electron deficient as compared to this one. Why? Because it is having a X group which is pulling the electrons, right, which is deactivating the ring. So if I compare normal benzene and a haloarene will react less slowly with electrophiles as compared to benzene. Okay, so that is what I have told you. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reactions in haloarenes occur slowly and require more drastic conditions as compared to those of benzene. Okay, so in benzene what happens, there is nucleophile, it is electron rich, it can easily react with the electrophile. But in case of haloarenes what happens, no doubt it is electron donating, but in case of if you remember, in case of halogens, the minus I effect is more dominant. Okay, so overall it is withdrawing the electrons, it is deactivating the ring slightly. Okay, when it is deactivating, this one will react less slowly, slowly with electrophiles. Okay, so we will see now what all types of electrophilic reactions we have. So 4 types of electrophilic reactions are there: halogenation, nitration, sulfonation and Friedel-Crafts reaction. Okay, so if I show you halogenation reaction, what is the reagent you have to remember here? So for chlorination, bromination, you have to use Cl2 with anhydrous FeCl3. So there is already a chlorine and the new chlorine will be attached at ortho and para position. The para product will be the major product. Okay, so remember, para product will be the major product. Similarly, for nitration, what reagent I require? Concentrated HNO3 and concentrated H2SO4. So nitro group will be attached at ortho and para position, and the para one will be the major product. Next we have sulfonation. So you have to just use concentrated H2SO4 with heating. So here what will happen? SO3H will be attacked at ortho position and at para position. Major product will be the para one. And lastly, I have Friedel-Crafts reaction. So in Friedel-Crafts you can add alkyl group also, acyl group also. What is acyl group? CH3CO. Okay, you can add this group also and normal CH3 group also. If you are adding this group, it is called Friedel-Crafts acylation. If you are adding only alkyl group, it is called Friedel-Crafts alkylation. Okay, so here you have CH3Cl, okay, with AlCl3. So CH3 and CH3 will be added and the para product will be the major one. And here if you have CH3COCl with AlCl3, so at ortho and para position you will have COCH3 and COCH3 group attached. Okay, so these are the 4 reactions, 4 electrophilic substitution reactions in case of haloarenes. Next we will see the reactions with metals. So here we have 2 name reactions, Fittig reaction and Wurtz-Fittig reaction. In case of haloalkanes, just a minute. Yes. So in case of haloalkanes, we have studied Wurtz reaction, right, where we have taken RX, Na and ether, and we used to get RR. So here what you have to take? Here you have to take a benzene ring, okay, ARX, and if you just take Na and dry ether, you will get AR and AR, okay, diphenyl compound. This is called as Fittig reaction. Wurtz-Fittig reaction. What is Wurtz-Fittig reaction? You take one haloalkane and you take one haloarene. In case of in presence of Na and dry ether, you will be mixing this R and AR. You will get a compound like this. Okay, so this is your Wurtz-Fittig reaction. It is very easy. Wurtz reaction, you have RX in in Fittig reaction, you have ARX. Here the product is RR. Here the product is AR. Then in Wurtz-Fittig reaction, just you have to mix both RX plus ARX. So what you will get? ARR. Okay. So with this, we are done with the complete reactions, chemical reactions of haloarenes. Okay, so now we have round 1 of quiz, and here we have 10 questions today. Okay, so you know the rule. You have to pause the question, you have to pause the video, answer the question in the comment section, then at the end of the 10 questions you have to put down your scores. Out of 10 in round 1, how much you have got. Okay, so let's start with the first question here. Which of the following reaction is incorrect? Let's see the first one. When you add Cl2 anhydrous FeCl3, so this is your first, that is halogenation reaction. We will get product always at ortho and para position. Here I am getting a product at meta position, so this will be the incorrect reaction. So option number A. Here I am getting NO2 group at ortho and para position. Ortho is minor, para is major, so that is the correct option. Here I have got sulfonation, I have got ortho product, and this is minor, so that is also a correct option. Next, nitration of this compound will give you. So you have this position Cl, Cl and Cl, right? So when you do nitration, it will be occupying either ortho or para. Now one ortho is blocked, one para is blocked. Only this ortho is left. So the nitration will happen at this position. So what will be the product? Meta, it will not take place, right? This is also meta. This is ortho position. So option number C. Okay. Next we have which of the following is more reactive in nucleophilic substitution reaction. So you have a compound, okay, you have a compound here and it wants to react with the nucleophile. This compound should be then what? Electrophilic in nature, right? How we can know? What do you mean by electrophilic in nature? It should be electron deficient. And how we can have electron deficient? By presence of electron withdrawing group. More the number of electron withdrawing groups, it is more electron deficient, it is more electrophilic in nature, it will react faster with the nucleophile. So here I have only one electron withdrawing group, that too at the meta position. So we want electron withdrawing group at the ortho position or at the para position. Here I have at ortho position, so this will definitely react faster. Here also I have 2 at meta position, this is of no use. Here also I have ortho and para. Here I have 2 electron withdrawing groups. That means it will be making the ring much more electron deficient, and it will be much more electrophilic in nature, so it will react faster with the nucleophile. Okay. Next, chlorobenzene on heating with NaOH at 300 degrees Celsius under pressure gives you. So we have just seen the first reaction, chlorobenzene, if you treat it with NaOH. Okay, so what will happen? This OH will replace this one and you will get phenol here. That is option number A. The hybridization of the carbon atom, carbon having CCl bond in chlorobenzene. This I have taught in very detail. So here we have this one. What is the hybridization of this carbon? Now as I told you, this carbon is having how many sigma bonds? 3 sigma bonds are there. So it is sp2 hybridization, option number B. Next, we have the end product Q in the following sequence of reaction. So first we have done Cl2 FeCl3. What is Cl2 FeCl3? It will add chlorine here, right? Addition of chlorine. So this is P. Then you have Na and ether. Na and ether is which reaction? If you have just remember, this is a Fittig reaction. So in Fittig reaction, what will happen? This one will combine with this one, right? So we will get diphenyl, that is option number C. Okay. Next, aryl halides undergo electrophilic substitution reaction slowly as compared to benzene, because this I have explained you very nicely. Let me just repeat. When you have aryl halide, okay, this is having minus I effect. It will withdraw the electrons from the ring. Okay, so nucleophile is there, electrophile is there. See, no doubt this is nucleophilic in nature, no doubt. Okay, and you have a plain benzene. This is also nucleophile in nature. Now when you compare these two, here we have a group which is pulling the electrons. So here we have a group which is reducing the electron density, right? We have a group here. So definitely if I compare these two, this is more nucleophilic and this will react better. So what is the reason here? Due to the minus I effect of the halogen. Okay, the minus I effect means electron withdrawing effect. So option number C here. Next, orthochlorotoluene can undergo. So if I have orthochlorotoluene, you have this group. Okay, electrophilic aromatic substitution, yes, it can definitely react with the electrophile, no doubt. Nucleophile, yes, it can react with nucleophile, but under certain conditions, right? Nucleophilic aliphatic reaction, no, it is a aromatic compound, right? It will not undergo aliphatic reactions. Free radical reactions, yes, that can also happen. So 1, 2 and 4, which is option number C here. Next, match the following. Okay, so here you have A, B, C, D and 1, 2, 3 and 4. Okay, so you have the first one Cl2 FeCl3, you got chlorobenzene, then it is Na ether. So this I have told you just now, we discussed Fittig reaction, so I will get biphenyl. So A has to be 3 and there is one option with A3. Let's see the next one. So here you have tert butyl and then you have given alcoholic KOH. You got a double bond and then you are taking HBr peroxide. So you have like this, okay, HBr peroxide. So bromine, if you remember from the last class, bromine will attach on this carbon, right? So what we will have? We will have this compound here. So what will be the product? This one, right? So that is B has to be 4. Next, if you see C, you have added Cl, then nitration you are doing, so you will get nitrobenzene. Then if you take it with NaOH and dilute H+, so in that case what will happen? The Cl will get replaced with OH and you will get this compound. So C has to be 2 and then D you will get 1. Okay. Next, 10th question, the Wurtz-Fittig reaction involves Wurtz and Fittig. So you have one Rx and one ARX. So it includes one molecule each of aryl halide and alkyl halide, option number C here. 2 molecules of aryl halide is Fittig reaction, 2 molecules of alkyl halide is Wurtz reaction. Okay. So with this, we are done with the first part of today's lecture, that is chemical reactions of haloarenes. 10 questions I have given you. Now you have to quickly comment down your scores. Okay, now we will move to polyhalogen compounds. So understand the meaning. We have in the classification we have studied about monohalogen, dihalogen, trihalogen. Polyhalogen means more than one halogen is present if in a compound, we call it as polyhalogen compound. Okay, so what all polyhalogen compounds we have in our syllabus? We will be studying about dichloromethane, that is like this. Dichloromethane means 2 chlorine groups are present. Okay, next you have trichloromethane, means you have 3 chlorine groups present. You have triiodomethane, that means you have 3 iodine groups attached. Okay, then you have tetrachloromethane, that means you have 4 chlorine groups attached. Okay, then you have freons. Freons means you have chlorine and fluorine attached to the same carbon. Okay, and then you have DDT. It is a chemical compound, as complex structure. We'll study about this. So basically what we are going to study about these compounds, we will be studying their uses plus their harmful effects. Okay, so this is completely you have to remember. I have given you notes on this. Please take a screenshot of this one, write it in point wise, and just remember their uses, especially harmful effects you can know, but uses are more important. Okay, so starting with the first compound, dichloromethane. It is used as a paint remover, as a propellant, as a solvent, and it is also used as a metal cleaning and finishing solvent. So these are some of the uses of dichloromethane. What is its harmful effect? It can be harmful at lower level. It can cause harm to the hearing and vision. At higher level, it causes dizziness, nausea and all. Then if you have direct skin contact, it may have a burning sensation, and if you have direct contact with the eyes, it can even burn the cornea. Okay, so this is very harmful chemical. Next we have trichloromethane. Okay, so trichloromethane, here it is used as a solvent for fats, iodine and other substances. It is also used in the production of refrigerant, that is R22. Okay, you know refrigerant are the coolants that is used in the refrigerators. Next, what are the harmful effects? At lower level, it causes dizziness. At higher level, to damage to liver, kidney, etc. Here something important from where questions have been asked. So if you have this trichloromethane and if you just keep it open, it is exposed to the oxygen, what happens, it gets converted to phosgene, COCl2, which is a very harmful gas. Okay, so that is why this trichloromethane should be kept in closed containers. Okay, because otherwise they will come in contact with oxygen and get converted to COCl2, which is called as phosgene, or a very harmful gas. Next we have triiodomethane. So it was earlier used as an antiseptic. Okay, but here you should be remembering that the antiseptic property are due to the liberation of free iodine and not due to iodoform itself. So what happens, iodoform formula is this one. But when you use it as an antiseptic, or when you apply it, it releases I2, and this I2 is used as an antiseptic agent. But this is the one which actually protects our wound from further infection. Okay, I2 is produced from this one, not directly iodoform is involved, but with I2. Next we have tetrachloromethane, that is CCl4. Okay, so it is used again as a refrigerant, propellant for aerosols and etc. It is also used to extinguish fire. Okay, this use is important. At lower level it causes dizziness, at higher level you have coma, unconsciousness, etc. Then direct skin contact, you can have severe burning. Environment, it also leads to depletion of ozone layer. Okay. Next we have freons. This is again important. Freons are the chlorofluorocarbon compounds of methane and ethane, collectively known as freons. Means in that same compound you have chlorine also, fluorine also. Okay, where it is used? It is used as a aerosol propellants, refrigeration and air conditioning purposes. Okay, and harmful effect, it is definitely a major pollutant in the ozone layer depletion. On the first class we have discussed that the haloalkanes and haloarenes can be life-saving drugs, and at the same time the deadliest pollutants that we have in this particular atmosphere. Okay, moving to the next one, we have DDT. So DDT is the the chemical stability of DDT and its fat solubility compounded the problem. So DDT was used as an insecticide. Okay, it was the first chemical insecticide that was discovered, but later it was banned due to it is not soluble or it is not easily biodegradable. So that is why it was banned. You can see here DDT is not metabolized very rapidly by animals. Instead, it is deposited and stored in the fatty tissues. If ingestion continues at a steady rate, DDT builds up within the animal over time. The use of DDT was banned, that's why. Okay, so these were certain 6 compounds whose uses and more importantly their uses, and you should also be remembering their harmful effects. Okay, so now we will be seeing some questions. So I welcome you to the round 2, okay, of the quiz sections, where we have 5 questions. So in the first one we had 10 questions. Here I have 5 questions. So total today's session has 15 questions, and we will see who is getting 15 out of 15 in today's class. Okay, so let's start with the first question. Which one is used as a paint remover? So I have discussed this one very detailed. So if you see, oh sorry, just a minute. Yes, so if you see the first compound that I have told you, dichloromethane, is used as a paint remover. So you know how questions can be asked from here. So that is why you have to remember these uses. Okay. Yes, so dichloromethane is your option number, yes, is your option number C. Next we have, which of the following is the commercial use of chloroform? Chloroform, it is used for the production of R22, we have seen. It was used as anesthesia. It is also used in pesticide industries. So all of these. Okay. Next we have the compound X. In the compound X, all the bond angles are exactly same, 109 degree 0.28 minutes, X may be. So when the bond angle is same, all the bond angles are same, that means these 4 groups that you have attached, these must be same. Okay, so A, B, C, D. If these bond angles are equal, then A should be equal to B, should be equal to D. Means all the 4 groups should be the same group. So if you see chloroform, the formula is CHCl3. For iodoform, CHI3. Okay, so there are 3 Cl bond, CCl bond and 1 CH bond. So all the 4 bonds are not identical. Here if I see, there are 3 Ci bond and 1 CH bond. So that is why this is also not, all the 4 bonds are not identical. Chloromethane, you have CH3Cl. Here you have 3 CH bond and 1 CCl bond. So all the 4 bonds are not identical. Carbon tetrachloride, here you have all the 4 groups correct. All the 4 bonds are same. So here the bond angle will be equal. Second last question. Auto-oxidation of chloroform in air and sunlight produces a poisonous gas known as. So I have told you this is a very important question. We get a gas like this which is called as phosgene. Okay. Next we have chloroform is kept in dark colored bottles because it reacts with clear gas. No. It undergoes chlorination in transparent gas. No. It is oxidized to poisonous gas in presence of sunlight. So that is why it should be kept in dark bottles where there is no sunlight. It cannot react. So that is why option number C here. Okay. So with this, my dear Bacha Party, today we have completed the chapter. Today we have completed the entire haloalkanes and haloarenes. So I want all of you to prepare the notes from the videos, from the lectures, and do revise this chapter for the next class where we will be solving KCET PYQs. So we will see that whatever we have studied in these 4 parts, with that are we able to solve the KCET questions or not. Okay, so I have given you as usual 3 homework questions. Okay, very easy questions are there this time. So 3 homework questions are there. If you read the lecture properly, you will be able to answer all of them. So please have a revision and then write down, then try the answers, homework questions, and put down in the comment section. Okay, so I wish to see more comments in the comment section, your answers, your response, and I hope that today's class was entertaining and you enjoyed the class. Do let me know in the comment section feedback that how was the class, did you understand everything or not. So that's all, and all the very best, my dear children. Please keep working hard, and we have very few months left. We will be preparing solid for the KCET examination, right? So all the best and bye bye.